Okay, let's talk about bootstrapping now. You know that you can sample with or without replacement. Okay, there's two things that you can do when you're sampling. So say we just got a sample of 300 teddy bears, okay? And it's a teddy bear factory. And from that factory, which is the population, we draw a sample of 300 teddy bears. And then from that sample, we're going to gather new samples. It's inception. Bear with me. I have visual representation so you can understand this. So let's just do the sampling without replacement first, and it's going to look stupid, and it's not going to make any sense, but bear with me. We're going to gather the sample that we just collected, okay? And one teddy bear at a time, we're going to randomly select one teddy bear, take that teddy bear out of our sample, bring it to our new sample, okay? Then we're going to randomly select new teddy bear. We take that out of our sample, place it in our new sample. And look, that we're not replacing those teddy bears, you know? They're like parents that went to buy cigarettes and never returned. They are away forever, okay? If we do that 300 times, okay, if we keep doing that 300 times, we're going to end up with the exact same sample, okay? And you can see the order is a little fucked, but it's a different order. But it's the same sample, right? If you remember, it's the same proportion as we had before, right? Look at this. So it's that, and it's the same proportion, same sample. It's like we're moving the entire sample over one teddy bear at a time, okay? Like, and you're saying, it's pointless. Why would you do that? Well, I'm only telling you this because I need to explain to you what sampling with replacement is, and this is what it is. Let's say you have that initial sample that you started with, and now one teddy bear at a time, we're going to randomly select, okay, one teddy bear. We're going to take it out, and we're going to place it in our new sample, okay? But now, we're going to leave an imprint of that teddy bear. We're not going to leave the teddy bear there. We're just going to leave a note of that teddy bear in the sample. We're going to take it back of our new sample and put it back in our old sample. So now, when we randomly select, we could choose any teddy bears, including the teddy bear that we just tossed back. You know, it's possible that we get the exact same teddy bear. It's unlikely, I know, but it's just for the sake of the example. So let's say we found the other same yellow teddy bear. We're going to bring it over to our sample, put it there, you know, leave it imprint, and then bring it back and toss it back. And if we do that 300 times, we're going to end up with a randomly different sample, okay? Because we're giving our sampling process a new chance to sample new teddy bears, a new teddy bear proportion. So we're basically creating a new sample from an old sample. It's very efficient. It's the same thing as spending those 7,000 euros, but now we're doing that with a single sample. And the only reason why it's possible is that we're using random error against random error. So let me tell you what that means. Let's say you have a population of teddy bears, okay? And this is the proportion of the population. And this is like, again, the divine view that allows us to view this population. When we draw our first sample, there's some random error, right? So probably we're not going to have the exact same proportion. Probably going to have one too many like blue bears, one too many orange, you know, teddy bears. It's okay. Now, when we use bootstrapping with replacement, we have some chance for random error again when we're drawing our new sample. So we're using random error against random error. That's what I'm trying to tell you. Because it could be that the new sample is actually more representative of the population than the initial sample. Like we actually have that chance. And if we do it enough times, we're increasing the chances that random error will fight random error. So this new sample that we generated with bootstrapping, with replacement, this is the bootstrapped sample. This is what we call it, okay? And let's look at the proportions. So here at the population, let's say the initial population proportion is 20%. Then you sample 18% of yellow candies because it's one too many blue teddy bears. But with bootstrapping, it could very well be that we return to 20%, which is a more accurate representation of the population than our initial sample, okay? So this is what we call the bootstrap sample. The one on top is what we call the initial sample, okay? So we can type it in. initial sample. Okay, this is what we call the initial sample when we're talking about bootstrapping. Now, let me tell you how we derive a bootstrapped sampling distribution, which is about the best kind of sampling distribution you can get coming from a single sample. We have the scheme. Let's look at the percentages. So we found the percentage of our first bootstrap sample. It's 20%, right? So what we do is that we can plug that 20% into a distribution, okay? And then we go and we sample with replacement once again 25 other times. So we get 25 other samples, okay? Sometimes you're going to have percentage 18%. Sometimes you're going to have percentage 22% proportions. But roughly, you're going to be plugging those into this distribution until when you do that 25 times, you're going to have a distribution that looks like a bell shape because we live in a simulation. Like, I don't know how much I can tell you this, but we always find the damn sampling distribution bell-shaped curve. It's amazing. So sampling with replacement is bootstrapping. Okay, this is what I want you to know. Big disclaimer though, bootstrapping is great, but we have to make sure that you have a representative initial sample, okay? So let's say if you draw an initial sample and randomly you have like, you know, this infamous proportion of yellow candies, which is so little, it sucks, then your bootstrap sample is also going to suck, okay? It's going to be a variation of that initial suckness, but it's also going to suck. So don't do it. Make sure that your initial sample is representative. How do you make sure that your initial sample is representative of the population? It's kind of difficult to know that. So that's the limitation of bootstrapping. You have to just believe and assume that your initial sample is representative of the population and not like a crazy exception like this one. Okay? Okay, now you can bootstrap any number in a sample. So now we bootstrapped a proportion, but we can bootstrap any number that you can find in a sample. Okay, this is what I want to show you. So let's start working with this idea of sample set. It's not a real term, I'm just making it to explain this idea. A sample set is a set of any numbers that you can find that you can use to calculate any other number to be bootstrapped. Very long sentence. What it means is that look at all these numbers you have available to you. You have standard errors. What are the numbers that we can find in the sample set? Well, we can find the mean, right, of our sample. We can find the median of our sample. We can find the standard deviation of our sample, this one up here. We can find the standard error, this one down here. We can find the regression coefficient of this predicting anything else, like if we were doing a regression analysis. You can find the upper bound of a confidence interval, the lower bound of a confidence interval, the square root of the average height. You get what I mean? You can get like your grandma's age plus 42 minus average height times 7,000. Like you can do whatever you want, whatever number you can find in a sample, you can bootstrap, okay? These are all numbers you can bootstrap. Can we bootstrap the mean? Yes. Can we bootstrap the median? Yes. Standard deviation? Yes. Everything you can bootstrap, okay? Deep breath. So let's think in sample sets and levels. Let's say you have this initial sample of the Dutch population trying to get their average height. And you have 1,000 people in your sample. The average height you found was 178. From that, you derive a sampling distribution. You find the confidence intervals for that sampling distribution. Great. So we're trying to estimate based on the average. So the average is the main number. The average is the number, the sample statistic. So we're going to sample with replacement. We're going to select one Dutch person at a time randomly, right? And there's a chance that we're going to have not one Johanna, for example, but 3 Johannas in this new sample or whatever, if Johanna is a person. And here we have our derived bootstrapped sample distribution. You can see the average here is a little different, 176, right? It's a new main number that we found. With that new main number, right, compared to 178, we can derive our own sampling distribution, right? Bootstrapped derived sampling distribution. I'm showing that. This is the entire set, right? So we can look for any numbers that we can find here. So like, for example, do you want to bootstrap the lower bound? You can bootstrap the lower bound. Do you want to bootstrap the upper bound? You can bootstrap the upper bound. You can do all those things. But focus, right? We want to bootstrap the mean, right? That's the thing we're trying to bootstrap. So we get that 176, and we plug that on our bootstrapped derived sampling distribution, right? And then we can do that again. 178, new sample with replacement. We find number 180, a little higher. And then we plug that in there. Okay, cool. Then we have a third one. We do that, 500 times, 500 times. Do that 500 times. Then you have this bootstrap derived sampling distribution coming from 500 bootstraps samples or bootstrapped sample sets. Okay? So this is what we call the bootstrapped sampling distribution. Here we're estimating the average height in the population. Okay. Also grammar, right? So remember, like if I decide to do my grandma's age plus 42 minus average height, initially, let's say I get the number of 23, okay? And then I get some bootstrap samples of my grandma's age plus 42 minus the average height in the sample. No, this time it's 25. This time it's 19. So it's this random number I came up with in my brain, and I'm just like calculating it for every sample set, and I'm plugging that into this new crazy nonsensical derived sampling distribution. Is that statistically sound? Yes, it is. You can do whatever you want with bootstrapping, okay? Because you're just replicating the same sample over and over and over again and creating a distribution, okay?